we're going to use this apparatus to measure the work function of a metal. Inside this photocell, there is a caesium antimony alloy, and that is going to be our photocathode. When illuminated with light through the small window here, the caesium antimony alloy cathode is going to emit electrons, photoelectrons. Now, if those electrons make it to the second electrode on the other side, then we can detect that flow of charge as a current by connecting a very sensitive ammeter here. That flow of charge can be reduced, of course, and the way we can do that is by removing electrons from that flow, by removing energy from the electrons so fewer electrons have sufficient energy to reach the other electrode. And that's what this battery is for. Inside this apparatus is a 9-volt battery, and we can control the voltage that we place across this photocathode. If we have a positive potential here and a negative potential on the other side, then electrons that are freed from the caesium antimony alloy, those electrons are going to be attracted back towards the positive and away from, they're going to be repelled from the negative. There's an electric field between the two, so the electrons are going to experience a force back towards the photocathode. The amount of energy that is removed from those electrons, the kinetic energy that's removed from those electrons, will be equal to the charge on the electron multiplied by the potential difference across which the electrons try to move. If the potential difference across this photocathode is 1 volt, then any electrons moving across that cathode are going to lose 1 electron volt of energy. 2 volts, 2 electron volts of energy that's going to be lost. Now, because the electrons are going to be liberated from different depths within the metal, there's going to be some electrons, photoelectrons, that are emitted with very high energies right from the surface of the metal, and others are going to be emitted from deeper in the metal. Those electrons that are emitted from deeper in the metal are going to have less kinetic energy because some energy will have been transferred in moving the electrons through the metal lattice in order to reach the surface. So the maximum kinetic energy the electrons can have is carried by the electrons that are emitted from the very surface of the metal. What that means is that if I apply a potential difference that is large enough, then even the most energetic electrons will not carry enough energy. Let's suppose, for example, that we have 1 electron volt electrons that are emitted from this surface. Just for simplicity's sake, let's say that's how much kinetic energy, the maximum kinetic energy is. But if I set 1 volt across there, then electrons will lose all of the energy they have just before they reach the second electrode. And so they won't reach the second electrode, and so we will not be able to detect a current. If I place half a volt here, then those 1 electron volt kinetic energy electrons can still reach the other side. Well, some of them can, some of them won't. The least energetic will not reach the other side. But the more energetic will. So these are a voltage, a potential difference, above which no electrons can be detected flowing from the photocathode to the anode. And we'll know that's happened, we'll know we've reached that potential difference when the current drops to 0, indicating there's no charge flow anymore. We call that potential difference that stops that flow of charge the stopping potential. We are going to measure the stopping potential. So in order to do this experiment, we need a few more bits of apparatus. Obviously, we need this one here. We are also going to need a voltmeter. That we're going to connect in parallel with the photocathode. We are also going to need a very, very sensitive ammeter. For that, I'm going to use this. I'm not sure how I can adjust the camera so you can see it. This is a galvanometer, an EDspot galvanometer. A very, very sensitive meter indeed. So we're going to use that. We're also going to need some way of changing the wavelength and therefore the frequency and therefore the energy of the photons that are arriving on this photocathode. And we've got coloured filters to do that. Red, green, and here it is, blue. We can use these coloured filters. The red will only let red light through. They are going to be the least energetic photons. So I'm placed over there. Only the least energetic photons are reaching the metal, so there's less kinetic energy carried by the electrons that are liberated from that metal surface, and so a smaller stopping potential will be expected. The green light has more energetic photons than the red light, so I'll expect a larger stopping potential to be needed, and the blue even higher still. Now I have got other filters. I've got loads of filter paper, in fact, but I've also got things like this magenta filter, this yellow filter, I've got a cyan filter here. And the problem with these filters is that they let through more than one wavelength. So that's not going to be very useful for us. We need monochromatic filters. I could use those and just use the more energetic photons that can pass through them. So the smallest wavelength that is transmissible through these filters. But the smallest wavelength transmissible through the magenta is just the red. The smallest wavelength transmissible through the yellow is just the red. I mean, you can tell that because I can still see the red filter quite clearly through there. And I can still see the red filter quite clearly through there. It doesn't look black. Cyan on the other side, on the other hand, well, the red filter now goes black. But the cyan will let through green quite happily, and it will let through blue quite happily. I mean, you can see the blue one really clearly. So there's absolutely no point using cyan. I have also got orange and violet. But similarly, I don't expect these filters to be monochromatic. And they might be, but I don't think they are. So it's not great having only 3 data points for 3 different wavelengths of electromagnetic radiation, for 3 different energies of photon. Not great, but it will be fine. We also need a source of light, and the light has to be a broad band. We need to have light with multiple frequencies, ideally a complete spectrum of all the colours. And so I'm going to use this tungsten lamp to do that job. The tungsten lamp uses a power supply. It's nice and bright. And red light, green light, blue light. So no problem. So what data am I going to need to collect? Well, the equation we're going to use is hc over lambda. That is the energy of the photon. It's going to be equal to the work function plus the maximum kinetic energy of the photoelectrons, which remember is going to be equal to the energy that we are going to remove from the photoelectrons by applying a potential difference across the photocathode. So the maximum kinetic energy of the photoelectrons is going to be equal to this stopping energy here, the charge of the electron multiplied by the stopping potential. So I'm going to need to be able to measure Vs. No problem, I've got a voltmeter, I can do that. H and C are constants. Phi is what I want to determine through this experiment, and E is a constant as well. So it is just lambda I need to know as well. I'm going to vary lambda and see what the effect of that is on Vs. So lambda is going to be our independent variable, and Vs is going to be our dependent variable. Probably spelled that wrong. No, it is an E, I think. E constant, C constant, H constant, so we can't really call those control variables because you can't change them if you wanted to. But phi is a control variable. We could use different photocathodes. We're just going to use the one. That's our control variable. That's what we're going to measure. Determine, through this experiment. Right, so how do I know what the lambda is for these coloured filters? Well, that's the trick. We're going to have to measure it. To measure it, I'm going to use a spectrometer. Now, that spectrometer is going to have a telescope that allows light to pass through it with a slit at one end. And the light is going to pass from my lamp through my filter and then through this telescope to produce a nice collimated beam. I'm going to place a diffraction grating, and I'll use one that has 300 lines per millimetre. And then we're going to use another telescope. And this telescope we're going to be able to place at different angles, which we will be able to measure. The light is going to pass down this telescope to the diffraction grating and then be diffracted in different orders. Using the largest order we can measure this diffraction angle and know the order. This is order 0, order 1, order 2, order 3. We're going to use an equation that usually gets studied in year 12, the Fraunhofer-Farfield diffraction equation for diffraction gratings, n lambda equals d sine theta. We know d is the spacing, the space between slits on our diffraction grating. Well, if there's 300 lines per millimetre, the reciprocal of that is going to be d. N is going to be 0, 1, 2, 3, as big as we can make it, not 0, that would be useless. And theta we're going to measure using the spectrometer, in order to determine what our wavelength is. So let us start doing that for each of the colours. Just before I do that, I want to show you what the spectrum from this white light looks like through a simple handheld diffraction grating, a handheld spectroscope. This is the handheld spectroscope. You can look through the tapered end and see spectra. Let's see what it looks like through this. Right, so through the spectroscope, we can see the different colours. Yes, it's a broadband spectrum, but if I take a red filter and place it in the way, you can see there's a bit of orange getting through there, actually. It's not a great filter. It's definitely cutting out the red, it's definitely cutting out the green, the blue, and a bit of the yellow. But the rest of it's getting through. If I've got here my green filter, let's just have a look at the green filter. Let's throw a little bit of blue there as well. And if I get out my blue filter, we're actually getting a bit of red through, but I don't care about that. So it'll give me the most energetic photons that we have to care about. So remember, higher energy means lower wavelength, which means closer to the right-hand side of the spectrum as it's shown on the screen. So that should be okay. We'll have to measure what that orange is, but that's going to be the most energetic one there. That should be okay because we're just getting just the near side of the blue through that green filter. And then there we're getting all of the blue basically through the blue filter. And interestingly enough, a little bit of red, but I don't care about that. So that's how we're going to have to measure things using the spectrometer. Let's get the spectrometer out. Just incidentally, while I've got this out, I've just switched the lights on. We've got these fluorescent light strips in this room, and you can see that the white light produced by our lights above us are producing a discrete spectrum. So that's just these lights above us that are producing that particular spectrum. Okay, let's get the diffraction, let's get the spectrometer out. So I think this is my favourite piece of apparatus, and I've done a video about it before. The slit is on this side, light is going to pass through the slit along this telescope here. Then that collimated parallel beam of light is going to be incident upon this diffraction grating. I can move, careful I don't move the grating around, I can move this arm around like this. When it's straight through, line everything up, when it's straight through, that's the 0th order, then I can find the 1st, 2nd, 3rd, 4th, as high as I can. And use the vernier scale here to determine the angles. Should be straightforward enough, and I should be able to just slip the different colour filters in there. Just like that, and it should work fine. So we'll see if we can get some sensible measurements. Let's get it all set up. So we've got our light source placed here with the slit, which I can make narrower, the telescope, and pan this down, diffraction grating. Looking through the diffraction grating, move this down. You will see, if I get it in the right angle, let's line this all up. There we go. You'll see there's the image of the slit. So put the diffraction grating in. Becomes difficult to see because I've got a lot of light around me. I could turn that off. Big light off. Still a lot of light around me, so it's not. You need to sort of shield all of this, I think. There's a lot of reflection, but it doesn't matter. Look, you can see right in the center there, if I put it in focus, there's the slit. Single slit. I can make that narrower if I want to. Really, I want to put some sort of box around this so there's less light coming off from around it. Right, that's fine. Now let's get the telescope lined up. Telescope is here, and I could hopefully move things around a bit. Pause. Again, some funny reflections that's making it difficult to see what I'm doing. But anyway, I've put the red filter here. As I move it around, there, that flash, that light there, not the bit there, that's just a funny reflection. That light there is the first order. If I keep going round, there, that's the second order. And if I keep going round, there's a third order, and keep going. I'm not really going to be able to see the fourth order, I don't think, not easily. So let's just go with the third order. Let's get the telescope lined up with where I am now. Measure these angles. First angle I have to measure is the angle for straight through. So let's get this crosshair lined up with the straight through beam. I need to make the slit narrower. Let's show you what I can see. Hopefully you can see that the telescope is going, the light from the lamp is going straight through to here. So that's going to be the 0th order. This is what it looks like. You see there's far too much light getting through. The reflection you can see on the top right of that is actually within my camera. You can't see that with the naked eye. That weird image that seems to appear, and as I rotate the camera around, it seems to move. But you can see where the crosshairs are. You can actually see two parts. That's because of the way I've orientated the bulb. If I rotate the bulb around a bit, I might be able to get a... let's rotate the bulb around a bit. I might be able to get a better, crisper image. I've lost it. Might be able to get a better, crisper image. Is that one single one? Yeah, that's better. That's because of part of the lamp design actually blocking some of the light. So that should be a bit better. You can see there's too much light getting through here. Far too much light. So I could make that slit narrower, which would improve things. Let's make that slit narrower. Am I making it narrower or wider? No, I'm making it wider. Let's make it narrower. Narrower slit. The narrower the slit, the less light gets through. Oops. I got no image there at all now. Alright, let's fiddle with this without the camera rolling. Not very clear on this screen, actually. When I look at it with my own eyes, I can even see the coil of the tungsten lamp. So it's... I'm not going to be able to get it much better than that. But that's okay. That's the 0th order. Let's go find that second, third order. Right, here's the second order. You can see the way the light is now smudged. It's still got those sort of horizontal lines indicative of the image of the coil, but it's now much more smudged out. The camera's doing funny things with the colours as well, but this is more yellow on this end, more red on the other end. So let's see if I can find a third order. That's the second. See if I can find a third. Oh, before I do that, I need to measure the angle of the straight through beam. What a wally. Let's measure that first. Let's get it back to the 0th order. Back to the 0th order. I've actually managed to get the coils of the tungsten filament appear in there. Really, I shouldn't see that. It should be a narrower slit, but it'll be fine. It'll be fine for what we're doing. It's quite a wide slit, but the difference in angle is going to be minor. Right, let's measure that angle off that vernier. Okay, we can see the vernier looks quite old, quite corroded. It definitely needs to be cleaned. The camera's saying move back to improve focus. Let's see if that actually helps anything. I'll move it back, everything's going to look a bit smaller as well. Might help the focus, but it's not going to help us see what we're looking at. That's as good as we're going to get. Right, what can you see? You can see 270 degrees, 275, 280, 285. Over here is 260. There's 265, and the vernier bit is past the 265. Now I can use a lens to help me see it more clearly. Of course, it's going to go out of focus on the camera. The camera's going to struggle to focus on anything like this. Try and hold it still. 265, 260, 267. It's about 267 and a half. I'm not going to bother going any more than that. I'm just going to call it 267 and a half. So to write down here, 0th, 267.5 degrees. That'll do, it'll do. We're only going to get some rough wavelengths anyway. Right, let's go find those orders. That's going to be the same now, that 0th order, for all the different colours. Not sure how clear this is. I think this is the 3rd order. I will double check, but as I move it, camera doesn't move with it. I'm right at the edge of the yellow bit. Remember, we're going to get yellow through to red, the smallest angle being for the smallest transmissible wavelength, which is, it says it's a red filter. It's actually closer to yellow. So I'm going to make a little table of results here where I'm just going to say color, order, and then angle. And so the color, this is the red filter. The order, I believe, is the 3rd order, and I can read the angle off. But that's the very edge, easier to see it with my naked eye, obviously. That's the very edge of the, so it's the smallest wavelength of light that's being transmitted through this filter. Let's go determine what that angle is. Let's adjust this. I can't move the telescope now, obviously. I've got it set up where I want it. Hopefully that's in focus. Okay, so what are we on there? The V part here is lined up nearly at the 250. Part of my camera's getting in the way. So 240, 250. Let's get the lens out, see if that helps. Not a lot of light here. Right, I might have to do this without the camera on so I can get closer. Right, I'm making it a little bit more than 247 degrees. I'm not going to be able to get any more accurate than that. I'm not going to bother getting more accurate than that. It's going to be the least of my worries in this experiment. It's going to give me a rough idea anyway. Right, I've just to double check that was the 3rd order. Then I'm going to do the green and the blue. And you don't need to see me do these. It's the same method as I've used before. So I'm going to skip ahead in the video. Except to say, I've just checked, it was actually the 2nd order, not the 3rd order. So my table of results currently looks like this. Bear in mind I have to subtract 267, or subtract this from 267.5 to get the actual diffraction angle I'm going to put in this here. So let's call that theta prime so I don't get the two confused. Right, let's do green and blue. That's the green filter. You can see the blue and the red getting through it. Absolutely terrible. Right, okay, let's do it. Okay, I'll skip ahead in the video. Right, I did all my measurements. I did it again and again and again, and this is what I've come up with. I couldn't see the point in measuring to any higher resolution than ½ degree. There was no point because things were so blurry because of how wide I had to have the slit. There really wasn't any point. This is how I calculated D. Remember, it was 300 lines per millimeter, so you just take the reciprocal of that, so 300 divided by milli. Reciprocal of that, so milli divided by 300, gives you 3.33 times 10 to the negative 6 meters. That is an M, excuse my handwriting. Using that equation to calculate these wavelengths, and I would have told you how we got the angle by using the spectrometer. Interestingly, these were quite similar in wavelength, really, or very similar in angle. There was a huge overlap, lots of blue coming out of the green. But it doesn't matter, let's get on with the experiment, which was to measure the work function. So let's get it all set up. I've got myself my galvanometer. It's going to get it center 0. Here's the apparatus we were going to use. I'm going to position the lamp somewhere over the photocell. I don't want it so close that I can't see the galvanometer screen, so perhaps I'll put it there. That's out of the way enough, I hope. Still trying to get that center 0. Right, the ammeter's connected. The galvanometer we're going to use is a very sensitive ammeter. It's connected via a coaxial connector. So there's the coaxial adapter. This is going to be connected to 0 volts to the 0 volts. Come on. let's say to the ground, to the zero potential side. Like that. Oops. And then the other part is going to connect to, oops, positive potential side. So hopefully we can see what's going on there. Still not quite on zero, so let's move it again. Ooh. A little bit closer to the right. A little bit fiddly. It's great when it works. A little bit closer to the right. Right, voltmeter. I need to connect the voltmeter up. Hopefully I'll connect it up so that you can see it. A little bit closer to the right. So negative side goes there. Positive side goes here. This is where I hopefully find out the batteries have not stopped working inside this instrument. This apparatus, hopefully it's not been left turned on. You can see the voltmeter screen on this corner there. Still not quite on zero. Go back, go back, go back. I'll tell you what I'll do. Let's block off the light entirely. It's a little bit easier if I actually put it on a scale. It moves more quickly. There, that's zero there. And hopefully this is connected properly. Oops, dodgy connection. That's measuring a current. There we are, clearly measuring a current. Block it off, current drops to zero. Move it, current is measured. So you can see that. No light, current drops to zero. Light, there is a current. Potential difference. As I increase the potential difference, I can get the current to drop. It's a dodgy wire somewhere. Let me find that dodgy wire. I think I've got it. So we've got a current. Increase the potential. It's now 0.28 volts. The current is dropped because the less energetic electrons aren't making it across that gap. Now even only the most energetic ones are getting across. And if I continue, the light's flickering now, but if I continue, look, at 1.1 volts, there's just not enough energy in those electrons to get across that gap. Ignore the flickering light. That's because I need to change the bulb. Right, so now let's get the stopping potentials. Paper here for me to write my results on. Let's get my stopping potentials for the different... Why is it showing no current now? Come on. Stopping potentials for the different colours. So start with red. Red on there. Knocked it again. I think it's a dodgy connection inside. Oh, what a nuisance. That means I've got to take the whole thing apart at some point. Anyway, red. Still a current. Not very much, but still a current. We can increase the sensitivity even further if we wanted to. Probably best not to. Right, let's increase the potential difference until that drops to zero. That is zero there. So let's increase it until we see a little bit of current flowing about there-ish. 0.44 volts, I make that on my voltmeter screen. So I'm going to put down, let's do this here, color, and then VS in volts. So for the red one, my VS was 0.44. And I could do repeats, but I'm not going to bother. Let's do the next color. Current goes back up. Get the green one. Pop it on there. Current drops back down, but it's not quite at zero. Now it's at zero. It looks like the calibration's drifted off a little bit, but it's not a problem. We'll just reduce it down until it moves a bit. Oh, it's around about there. That's pretty much zero. About there. Okay, so I'm getting about 0.78 volts for the green filter. It goes up again. Let's get the blue filter. It barely moves. You can see why we need to have a very sensitive ammeter here. So put this in there, almost completely drops to zero. That's zero. Again, the calibration's drifted off a little bit, so let's move that there. Make it a bit easier. Let's drop it down until we see current. Lots of current. Let's try that again. Dodgy connection. I'm going to poke around with it. Lots of current. Blue one, current drops. Increase potential until the current is 0. That's pretty much 0. So let's decrease the potential until we get a teeny bit of current detected. Oops. So around about there. Seems lower than it was last time, so I'll do the green one again. Looks about 0.81. It's barely any different to what I had last time. I'll keep going. Okay, so I've got some data. I'm not happy with it. I'm going to try the green one again, because I'm not convinced it was giving me sensible results. Oh, that's much lower that time. This time it's more like 0.61. I think the previous one was nonsense. And so this is how we do it. When we're not convinced by the results, I think there might be some sort of anomaly, we do them again and again and again until we're happy with them. You don't need to watch me doing that. I'm just going to keep on fiddling with it until I've got some sort of consistency in my results. So after fiddling with it again and again and again, getting data that's consistent, making sure I turn the lights off in the room so another light was leaking underneath the filters, things like that, I got voltages like this. I've calculated the reciprocal of lambda already, because I'm going to need that. And what we're going to do next is use the equation hc over lambda, I'm going to call it c naught, over lambda, that's the energy of the photon, equals phi, the work function, plus EVS. Fine. We need to get that in the form y equals mx plus c. Well, this is a variable, that's a variable, but everything else is a constant. So if I divide through by hc naught, I get 1 over lambda equals, I'm going to write it in this form, for what I think are going to be obvious reasons, like that. I get another coloured pen out so you can see that I've got, that's a variable, and get another coloured pen out. That is all a constant, that is all a constant. In fact, this is in the form y equals mx plus c. That's why I called the speed of light c 0. So if I plot a graph with 1 over lambda on the y-axis, and Vs on the x-axis, I should get a straight line. The gradient of that straight line would be E over hc naught. And the intercept should be phi over hc naught. So phi should be equal to the intercept multiplied by hc naught. No problem. Now we need to plot a graph. Okay, so with these data, these are the scales I've chosen. Notice that I've got lambda, but it's to the -1, so that's the reciprocal of lambda, which is what that is. Now I have to be quite careful with the units that I put in here. Times 10 to the -6. When you take the -1, that becomes 10 to the 6 on the bottom, which is what the scale is. So I think that's right. Across here on the x-axis, we've got potential difference. Now we can plot our points. Just 3 points, it's not great. If I take my ruler, need a 30 centimetre clear plastic ruler, you see they lie pretty much on a straight line. In fact, on this occasion, a 30 centimetre clear plastic ruler isn't even quite long enough. That's probably the best line of best fit we're going to get. Not just connecting the first and last points. Now we need to pick the points that we're going to use for the gradient calculation. I'm going to pick points that make it quite easy to read off the scale. That looks quite easy. I'm looking up this end. Let's go with that one there. Now, the usual way of indicating the points you're using is dotted lines, so I'll add those. And do be careful when drawing those lines. You don't want them to wander off. They should be perfectly horizontal, following the grid lines, perfectly vertical, following the grid lines, which they are. Okay, now we're going to write down the coordinates. I do think this is a useful step. So 0.7 volts and 1.9 times 10 to the 6. That's what that means, 1.9 times 10 to the 6. Do the same thing up here. This is 1.31 Maybe I should have called that 0.70. And y-axis, a little bit more tricky, 23, 23.5, 0.6, 0.7, 23.75 times 10 to the 6. There we go. So now I've got those, I can do my gradient calculation. I'm going to write my working directly onto the graph. That's the best place for it. Now let's get this horrible calculator thing. Ew, I hate this calculator. To do the calculation. And that gives me 778,689 units will be volts to the -1 and meters to the -1. Interesting units. Now remember what we're going to do with this gradient. This is it here. In order to get the y-intercept, we need to know what the gradient is because it's a false origin. We can't just read off the y-intercept. It's the y-intercept we're interested in, so I'm going to use this gradient to determine the y-intercept. So the intercept, I'm going to write it like that so I don't get confused with my c's. That's why I've got a c here. My intercept is going to be the y value. Let's use the maximum value I've got up here, 2.375 times 10 to the 6. Subtract the gradient, which I can just write down, multiplied by the x value, 1.31. And I can plug that into this horrible calculator as well. There it is. And the unit for that, 1.4 million-ish, the unit for that is going to be per meter. Again, everything has a unit. Now the intercept has to be multiplied by h and c to determine what phi is. So I might as well just bang that straight into my calculator. So that times by 6.63 times 10 to the -34 and times by 3 times 10 to the 8. And that gives me in joules 2.69 times 10 to the -19. And to get it into electron volts, I'm going to go ahead and maybe I'll edit that out later. I'm going to go ahead and divide that by the charge on the electron. That gives me, in electron volts, 1.68. Should be about 1.65, I believe. So 1.68, not bad at all. And we can check things. We can take that gradient and we can calculate what Planck's constant is based on the gradient, because E was measured by Millikan's experiment and C is measured by Fizeau, or Heinrich Hertz, or James Clerk Maxwell's prediction. We know C, it's well known. So we could do E divided by C, and then the gradient multiplied by C divided by E should be 1 over H. Okay, so do the reciprocal of that. So, okay, we could check that H matches what it should do. I'm not going to do that now. That wasn't the point of this video. The video's gone on long enough as it is. But there we go. The work function of a caesium antimony alloy, pretty close to what it should be.